So for our next example, what I want to point out is that the idea of one function being inside another is really just a very special case of a more general principle, which is that I can wrap one function inside another inside another. I guess it's a little bit early for Thanksgiving, but I've never eaten this, but I suppose some of you have probably eaten turducken, which is what is that? A chicken wrapped inside a duck, wrapped inside a turkey, or something like that. So you can nest things as much as you want. So basically, what we have here is the chicken wrapped in a duck wrapped in a turkey. We have tangent inside cosine inside the sine function. So the question is, how are we going to differentiate this? This is where the whole the f the f prime g prime rule, it kind of breaks down. It's not that I can't write out a rule like this involving f, g, and h. It's just that it's easier to think of yourself as working from the outside in. So take a look at the outside function. The outside function is sine. So what I want to do is I want to treat this like I'm taking the derivative of sine. Basically, what I'm going to do is it's like I'm taking the derivative of sine of x and just treating this thing in the red bracket as if it were x. Then I'm going to multiply the derivative of that. So the way to think of this is that this is equal to derivative of sine is cosine. And now, whatever's inside the sine, I'm going to put it inside cosine because it's like I'm just taking the derivative of sine. So that's going to be cosine of tangent of u. Sorry, I should be making clear I'm taking the derivative with respect to u, not x. Apologize for that. So this is cosine of tangent of u. And now, because this wasn't just a u inside here, because it was cosine of tangent of u, what I have to do is now multiply it by the derivative of the inside. In other words, by cosine of tangent of u. Fortunately, this itself is just another chain rule problem. What we have here is we have that inside function, which is tangent of u. So, just to keep everything straight, I'm going to rewrite all of this. This is cosine of tangent of u times the derivative of cosine of tangent of u. So the derivative of cosine is negative sine. And I'm just going to treat the thing in the brackets. It's just like I'm taking the derivative of sine x, and I'll deal with the thing inside later. So this is going to be the derivative of sine, negative sine applied to tangent of u. And then I have to multiply that by the derivative of the inside. You see how I'm working from the outside to the inside? So finally, we can do one more line. This is going to be cosine of tangent of u times negative sine of tangent of u times the derivative, sorry, I wrote that as d over dx. I meant to write d over du. This is why I should do all problems in x, because I keep forgetting. I'm trying to give you the idea that it can be done in different variables, and then I forget to change the variable. Okay, so the derivative of tan u, we know the derivative of tangent is secant squared. There's nothing else to do here. This is just going to be secant squared u. And there we go. We have, I need like one more parentheses there. Okay, so there we go. That's the derivative with respect to u of sine of cosine of tangent of u. What does one do with a function like this? As far as I know, the main purpose of such a function is to demonstrate that calculus works. I don't know of any use for sine of cosine of tangent as a function, but if we had a use for it and we needed for some reason to find the slope of the tangent line, it's kind of an overuse of the word tangent. If we needed for some reason to find the slope of the tangent line to that function, we could use this derivative. The rule works. This creates the derivative function.